integration long division. So up until this point, we've integrated a lot of different functions. So we had trig functions, we had trig inverse functions, we had exponential functions, we had log functions, and then we had our polynomials. In a lot of our polynomials that we were integrating, we were sometimes given products and quotients, which were easy to integrate once we multiplied out the brackets if it was a product, or if we factorised the top and the bottom and simplified our quotient. So in the following examples, we're not going to be able to simplify our quotient integrand, and instead what we're going to have to do is use long division. So in other words, there will be no common factors between the top and the bottom, between the numerator and the denominator. So if we look at our first example here, we're asked to integrate 3x plus 2 over x minus 1 dx. So we do our rough work to the side. So we're taking x minus 1 and we're dividing it into 3x plus 2. So x goes into 3x 3 times. If I multiply that back out, 3 by x is 3x and 3 by minus 1 is minus 3. So I change my signs and I end up with 5 as a remainder. So normally when we're doing our long division, we don't end up with a remainder. So basically, I now put that back in here and I say, well, my integrand, when I divide x minus 1 into 3x plus 2, it goes 3 times, and I'm left with 5 over x minus 1, which is my remainder on the top. And now I just integrate as normal. So of course, we have to look at integrating with respect to x. So if I integrate 3 with respect to x, I get 3x. And then this function here, we have to recognise and identify what is it when I integrate. So if I look at my maths tables, page 26, what I can see is this function here, 1 over x, and when I integrate it, I get the natural log of x. So therefore, some people may not recognise that as 5 over x minus 1, and therefore, really, I could write that as 5 times 1 over x minus 1, and then it becomes more obvious. So it's always 1 over a linear function. So this x, it'll always be linear as the denominator if it's natural log when I integrate. Okay, so if I integrate 5 over x minus 1, that's going to be 5 times natural log of the function, which is x minus 1, divided by the derivative of x minus 1, which is, of course, just 1. So therefore that becomes 3x plus 5, natural log of x minus 1, and of course there's no limits here, so it's just plus c as my answer. If I look at a second example then, if I'm asked to integrate 2x squared minus 1 over x squared plus 1 dx. And again, there's nothing common with the top and the bottom. So I do my rough work to the side. And I say, well, I'm going to divide x squared plus 1 into the top, which is 2x squared minus 1. So x squared goes into 2x squared twice. If I multiply that back out, we get 2x squared plus 2. And if I change the signs, I end up with minus 3 as a remainder. So therefore, when I divide x squared plus 1, I should say, into 2x squared minus 1, I end up with 2 minus 3 over x squared plus 1, and I have to integrate with respect to x. So again, if I integrate 2 with respect to x, I get 2x. And again, I have to spot this. What is that going to be? So again, if I go to page 26 of my maths tables and I try and recognise this function, what you'll see is it's 1 over something squared minus something squared, which is our tan inverse function. Okay, so therefore that's 3 times 1 over 1 plus x squared. Might make it easier to spot. So in other words, it's 1 squared plus x squared. So that's going to be our a and our function of x. So therefore, if I integrate, that's going to be minus 3 times tan inverse of x over a. So x over 1 and then plus c. And because a is 1, 1 over 1 is just 1. So therefore that just simplifies to 2x minus 3 tan inverse of x plus c. And of course, in the sheet that I've attached on Teams, there'll be a couple of these that have limits in it, so applying what you've done in the first class. Okay, so I'll upload the solutions to the worksheet then later in the day.